daily data over 30 years or 40 years. And you get these beautiful seasonal dynamics, but what are the trends underneath there? And you can look at trends by getting rid of seasonality, by a method called, you have several decomposition methods. So seasonal trend decomposition method in R is one of them, but there are other ways to get rid of the seasonal signal. And I just call it getting rid of, but in a way, seasonality is also very useful. But in this sense, you get rid of an average seasonal signal. And then you can start looking at trends by doing trend analysis, but it's called temporal segmentation. So you detect basically breaks in the time series and then fit a trend between the breaks. And we don't have time to look at the statistics, but if you have questions about it, feel free to contact me or Dainius. We are maintaining the BFAST package in R still. And also for these breaks, you get these confidence intervals on time of break event, which you can see here. By the way, so the smaller it is, the more sure you are about the time of the event. But like, for example, here, that can be an interesting one, because that was a big, almost not visible in the time series, but by decomposing, things become a bit more clear, a bit more understandable. And the remainder is the thing that is then left over at the end. So the sum of ST, TT, and ET, so seasonal trend and remainder component, is the time series again. And that's the beauty of the method. Just by simply summing up, you get the original time series again. And you can do simple things like, for example, detecting time of a deforestation event in the first slide. In the first time series, this is MODIS data, shorter time series from 2000 until 2010. But you can also map drought events. For example, here is a drought event, a big dip, and then you have time of drought, for example. But in Wageningen University, we were doing a lot of research on mapping illegal deforestation and trying to detect changes as fast as possible based on any kind of satellite data, Sentinel-1, Sentinel-2. And then I give the floor to Dainius because he took some steps.
Yes. Hi, everyone. I'm Dainius Masiliunas. I am a lecturer at Wageningen University. And during my PhD, I was working to advance some of the BFAST methods, and I developed BFAST Lite. So it's basically what you just heard about BFAST, but it is more useful for large-scale analysis. So the original BFAST does this decomposition to season and trend components, but that takes quite a long time to do. It's also an iterative process, so you might need to have it run several times until it converges. BFAST Lite is a simpler method to detect breaks that doesn't do the decomposition, but rather it tries to fit in a regression the components for the seasonality and trend all together in one step. So the nice thing about it is that you only need a single pass to detect breaks, all the breaks in the time series. And because it is based on a linear regression, it does not require having a gap-filled time series. So we don't need this kind of very fancy gap-filled data that Tom was talking about yesterday. We can just use any time series that just has been masked of clouds, and it will work. And because it can handle missing values, it also runs much faster. It's an order of magnitude faster compared to the original BFAST. And it also provides more parameters and statistics. So you can see here, turn on the laser pointer, there we go. So here you can see the break magnitude that is being highlighted. So for every break, we know how big is the change relative to one another using several statistics. And there's also more parameters that you can set. You can change what statistic you use to detect breaks. So you can get more breaks or fewer breaks depending on your area of interest. And you can also, for example, choose whether the seasonality should be modeled using these harmonic functions or using seasonal dummies. So you select like how many seasons you have per year, and then it gets fit based on the data. And so this is part of the new release of the BFAST package on R. And nicely enough, in the last release, the improvements were done not just by adding this new BFAST Lite method, but also the original BFAST function was also upgraded. Thanks to also Marius Appel from Münster University, who was working to improve the R code by translating the critical paths to C++. So actually the original BFAST is also now faster. And using this STL Plus package allows the original BFAST to handle some missing data as well. Previously, it couldn't really handle any missing data at all, and now it can handle some, but not as much as BFAST Lite. So now BFAST Lite has kind of become the go-to solution, at least for large-scale processing. The one downside that it has is that since we don't do this decomposition, we cannot tell apart breaks that are seasonality-only breaks or trend-only breaks. But that was something that users were rarely using anyway, because most breaks are in trends and not in seasonality. And there's a paper that I wrote about BFAST Lite that you can read more details about. So what we are using it for, so this was already implemented actually in the Copernicus Global Land Service land cover map, that we ran it actually for the whole globe on MODIS data. It took like a week or something, and it worked out on the cluster at Vito. This would not have worked with the original BFAST. That would have taken months. And what we used it for is to constrain areas of possible change. So if BFAST Lite detected a change, then we would also cross-check with the machine learning output for the different dates. And if there was a change also in the machine learning output, we would say, okay, this is probably a real break. But if BFAST Lite said there's no break, then it's very unlikely that there was actually any break. What I'm working on right now is another paper about how we can actually use BFAST Lite as a post-processing method, which is quite an interesting way to actually get smoother time series. So BFAST Lite can detect changes, but you can also get these individual components. So as you were seeing in the previous slides, you can get a time series without the noise. So really the model seasonality plus the trends, which means that you get a much smoother output, which is also more realistic because land cover doesn't change that frequently. But you still keep big breaks and you can still see the seasonality if you're interested in that. Or you can just get trends only and then see long-term changes. So that's what I'm working on right now.
And Dainius, you said you run it on the MODIS EBI or?
Yes, so we chose several vegetation indices. It was running on NIRV in the end. So the NIRV vegetation index for the whole globe, yeah.
8-day or monthly?
I think it was 16-day product, if I'm not mistaken.
But doesn't have a 16.
Well, yeah, it was aggregated on the Vito platform, but it's all in the ATBDs if you want to see all the details.
So 1 week just to run one variable?
Yes, so for every pixel detecting all the breaks in the whole time series, yes.
And it worked with the NA values?
Yeah, yeah.
And it worked also for the Northern Hemisphere?
Yeah, it works everywhere.
Canada? Yes?
Yes.
Are there maps somewhere we can look?
So it was produced on the platform. We had a copy somewhere, so it's there, but it was not published as its own data set. But it's relatively straightforward to rerun it because it's literally just running the function on the MODIS input time series. No.
You can run it on our own system. Let's see.
Yeah. Okay, now giving the floor back to Jan.
And here's another example of some simplified function applied in the Google Earth Engine. So the Google team has implemented the break detection functionality, and you can apply it on time series and easily scale it. And here, Jessica, a PhD student, has written a paper about landscape restoration and regreening and applied a simple function, just looking at one major change over long time series. And on the map that is shown, these are landscape restoration plots that she then automatically identified and also validated based on field data in Africa. Yeah. Almost the same. The break detection is very similar, but not identical. Yeah. That's a good question. So it's there. The code is open. Otherwise, you just do work. Yeah, they did the work, so we didn't do it. I'm always quite reluctant doing the work and implementing that. But in this case, it's simplified and easy that you can use and easily scale data and get scientific output out of that. Yeah, but the Google engineers spent some time on that.
Yeah, I can add a bit to that. So the BFAST monitor code on Google Earth Engine, so the source code that implements the function is open source. So it is not included as part of Google Earth Engine itself. So it's not like a closed function. You need to kind of load a library, which includes the actual code in JavaScript, and then you run it, and then you get the output. So you actually know what you're running in this case. You just don't know the background of what Google does with their own servers, basically. Well, it's faster by virtue of Google having lots of servers to run it. So, so we can't check which one is faster because the implementations are different. So it's not like you can run the JavaScript code on your own laptop because you actually need the Google Earth Engine backend to be running.
So just a comment on it, because I remember I used it a kind of long time ago, this land trend R. And as far as remember, they implemented it in the backend. And when you implement in the backend, it's a bit difficult to know if it's open source or not, because probably they use a Java implementation that runs in the Google Earth backend. And in this case, you don't know exactly. But if you import as a library in the JavaScript, you can still keep the code open.
I'll come to BFAST monitor right now. That is a classification, so also post-classification option that we implemented. That's in R to determine, so you can also classify the results into classes like linear increase, linear decrease, but also negative reversal. So if you first have an increase and then a decrease, that's yellow, or a positive reversal, for example, first a decreasing trend and then an increasing trend, you can map these types of changes and map them spatially. And then that really can show you interesting patterns. So constant increase is a constant growth of things. So you can really reuse that in the context of resilience and recovery. So these are simple ways to do post-classification, basically, post-processing. And then BFAST monitor is a specific function to look at the end of a time series and to check whether or not something abnormal has just happened in near real time. Just on the latest data or observation that you have, a new satellite image, you can check whether it's abnormal compared to all the images that you've got previously. And you do that basically by fitting a model based on the data. That's the blue model. And then you have a blue prediction, basically in the gray zone. You predict that into the future, and the new data is the red data. And if it differs a lot from the blue data, if the red data, that is the new data, differs a lot from the blue data, then you detect a change. So that's detecting change in near real time. And that's what we use to apply via R or Python. It's a simple way or a simplified version of BFAST just by looking at change at the end of a time series, but you can apply that to detect disturbances in near real time based on time series, basically. That was a later publication in 2012 in Remote Sensing of Environment, Near Real-Time Disturbance Detection. And that, as Dainius explained earlier, by Hamuniela, by Eliakim, was implemented in Google Earth Engine, also with the help of Andrei. And you can easily scale it. There are some apps there. And look at time of change in near real time and also magnitude of change at the end. Tracking historical forest disturbances using Sentinel-2. And then you can check the time of change at the end, for example, in the color. Blue is recent change, yellow is rather change in 2019, for example. And then you can apply this function, that's R function, via a user-defined function via OpenGeoHub. Similar ideas, and we applied it on Sentinel-1, a paper by Matthias Schramm in the OpenGeoHub consortium, also back in the days. Milutin, you also helped there. And then CEPAL, a very nice initiative by FAO, Linux environment. So it's a Linux environment, but they do the computation on Amazon. But you basically have your virtual machine and you can launch instances, GPUs, etc. And you can run BFAST monitor GPU version, for example, there, and apply it over time. And so the GPU version has been done by Fabian Giesecke. We have a computer science paper on that, and then even more recently, the STL, so the seasonal trend decomposition method, has been rewritten by OpenCL, but also Footarc on GPUs. So, but that's the simplified version. So we focus on BFAST monitor here.
Jan, one question.
Yeah.
Will this only work for NVIDIA GPUs or also for AMD?
I don't know.
All right. Probably only NVIDIA.
NVIDIA, I think.
Yeah. So I mean, it would be nice to also have an AMD version, since, for example, Lumi is purely AMD based.
Yeah.
I mean, here it does say Pi OpenCL, and that's AMD as well, so it might work. We need to ask the people who implemented it.
Yeah, but probably the optimization.
All the code is there on Google Colab.
Yes.
That's an example for Africa where we applied it. And then I'll leave the floor to Dainius. There's some recent papers. People applied for all sorts of applications.
Yes, so the new developments, including BFAST Lite, have been taken up by the community already. So actually, we have a pretty large community of users of the BFAST algorithms who are really using it every day for their change detection needs, because BFAST is a pretty mature, well-established algorithm. And some of the latest papers about the developments from the others are listed here. So it has been used for example, detecting turning points in ecosystems. That's one of the bigger research directions that have been making use of this BFAST classify recently. Here you can see an example from one of the papers where they really showed like areas in one of the provinces in China where you have either like monotonic increase in the vegetation index or decrease, or also whether there's an interrupted increase and things like that, and getting all kinds of statistics about long-term changes in those areas, which is quite a nice way of figuring this kind of things out. What we are going to work on in the future, because this can only give you the turning points for one major break in the time series, but with BFAST Lite, we can actually now do that for all the breaks in the time series, not just the largest one, which means that a break that is more recent is usually more interesting for the users because it's the one that you can actually do something about. And so we'll try to implement this on BFAST Lite and then see how it works and what new things we can discover with it. And the other thing that has recently been done is also some comparisons with BFAST Monitor and BFAST Lite, how they work together. And also, in this paper, they actually created a version of BFAST Monitor called BFAST ML2 to make it a little bit similar to how BFAST Lite works as well, in the sense that even though BFAST Monitor was made to only detect one break at the end of the time series, if you run it multiple times, it will detect multiple breaks based on a sliding window, but then they overlap. So this method is basically trying to find a common break using many iterations of BFAST Monitor. And it also has interesting outputs, but we are still to check how good it is compared to, for example, BFAST Lite in real application. These are all kinds of things that some noise in the okay, thanks. Thanks. And so for the upcoming features that are in fact based on the wishes from the user community, one thing that we would like to do is to do an automatic selection of an appropriate harmonic order. So when you have a time series, it is important to make sure that you model the seasonality appropriately. And right now you need to manually specify whether it should be really closely following your data or whether it should be like only one sine wave per year, things like that. But we can actually fit several things and then automatically determine which one is the better option. So we'll need to experiment with that and see how it works in practice. And then we also want to make it easier for the users to set their own statistic for detecting when is a change considered to be a change. We have implemented several statistics in BFAST Lite, but we could also make it possible for the users to make their own. And that could be quite useful for some of the applications. Then this BFAST classify support for BFAST Lite was how I was just talking about, where we can detect how the changes have happened for all the breaks, whether it's an interrupted increase, for example, or decrease and things like that. And then we also have a quick structural test that we can run even before running any of the BFAST algorithms to just quickly screen areas where we think there's no change whatsoever. Then we save a lot of time. So the structural change test is kind of similar to BFAST Lite in that it's to BFAST Monitor, where it's like super fast, not very accurate, but it's super fast. So you can save also a lot of time for these global applications by just skipping places where you're sure that there's no break anyway. And in the future, we might also integrate BFAST into the SIS package, which is developed by INPE in Brazil. And it's actually very handy for land cover classification. And BFAST could be very well suited for improving this updating of land cover maps, and perhaps also in this ability to do post-processing for land cover. So that could be a very useful integration. And also, well, if you have more ideas, feel free to just let us know on GitHub following this link. This is where we're developing the package, and we will look into it, and maybe it will be there in an upcoming release. So to learn about how to use it in practice, we have a very nice tutorial in this link, which shows both BFAST Monitor and BFAST Lite, and it explains the differences between the two algorithms, and with some hands-on examples of how you can really use them. And also, if you want to learn more, you can take a look at the source code, and we're trying to develop also a website for it. It's still very bare bones at the moment, but we will need to add more content in the future. Yes, I think Jan can continue for the last slide.
Thanks, Dainius. And then these are two papers in green that have been published in 2022 using related algorithms or looking at recovery metrics derived from optical time series over tropical forest. And a related team together with Milutin, assessing Amazon rainforest regrowth with JEDI and AST2. So then overall, as a take-home message, BFAST open source collaborative project started off with looking a lot at data and time series and dynamics. So I can highly recommend R because it's quite powerful for data visualization, very handy, and also strong on statistics. So it's a nice environment to have fun and develop things, and then scale it up in any kind of environment. And so focus on open source, as I see it's used a lot, excellent for collaboration and within a Linux environment. We started up the geoscripting course at Wageningen University, full on Linux, within Linux, etc. And then I can highly recommend you to also, besides scripting, once in a while, take time to relax and go for a walk in nature and map some trees with the app of Milutin. Thanks a lot for your attention, and if there are questions, let us know.
Okay, I use the microphone. If you, the way I see it, it's if you have issues with detecting the breaks, then everything gets complicated, right? Because the detecting break is the first step. So if some transitions are more gradual, and you pick up a break, then everything else also propagates, no? All the problems.
Yeah.
So is there any uncertainty assessment of how well you detect break? Do you do any probability distributions or quantile or the prediction intervals?
Yeah, you have several ways. There is a whole bunch of statistics involved on the certainty of the break itself. You can also use different criteria, etc., and also set criteria on once the break is detected on the confidence interval. Also, if it's too wide, you can even discard it, for example. And you have different tests, also break tests. You have simple ones also, as Dainius also explained. You have these very simple functions that you can apply even before the full breakpoint detection function. Even before you start detecting the time of break, you can just do statistics on whether there is a break, yes or no, even not knowing when. So
and one more question about the latitude and elevation. It looks to me it will be useful to incorporate that in the modeling. So for every pixel, you know the latitude and elevation, right, for the whole world. Because that determines the seasonality and things, northern, southern hemisphere.
Good. Yeah. If you do that globally.
Yeah, I can add a little bit to actually both of those questions. So one thing to keep in mind is that if you're doing land cover analysis and you want to do break detection, you still have these two parts. So break detection is one part, but the machine learning output is the other part. And so if you are trying to do the modeling, it is very useful to include indeed the latitude and the elevation in the machine learning part. For break detection, it doesn't help much because you have to have then a time series of these things, which of course for latitude makes no sense. And for the height, it would be great if you had it, but usually you don't. But if you do have something that is related, maybe for example, weather data, you can actually also include it as one of the covariates when fitting your data in the time series in BFAST. That is a possibility. Yeah.
Can you specify breakpoint?
Yes. So
So what I can recommend that would be super nice to do. You have to only be careful and check the density of the measurements of the Landsat, because in some areas, of course, you don't have a lot of observations. So you have to, before you apply the algorithms, do some tests on data gaps and amount of good quality observations and things like that. But if you have a nice number of measurements, so Landsat images for a certain location, then yes, that would be nice to apply it globally and scale it up. And then you could look at trends, for example, within the stack of Landsat images globally. That would be super nice. Maybe look at C++ simplified version. There can be some tricks. Yeah,
so it should work. Yes.
Without light, decent ways. Yeah.
By the way, we are working now should be better than the plan.
Yeah.
What is that?
Yeah, I actually double checked exactly how we did it. And indeed, we aggregated everything to 16 days. We actually checked the 8 days versus 16 days, and there was no difference between them. So we might as well just use 16 days to make it faster. And we tried 3 vegetation indices. So it was NIRV, NDMI, and EVI. And it turned out that NIRV was actually the best at detecting changes in all of the land cover classes, whereas NDMI, for example, is useful for forests mainly. Yeah, and then, so yeah, you can run it on a large scale. And the biggest issue actually with these detections is not so that we're missing breaks, but rather we're usually over predicting breaks. And that's why it's a good combination with machine learning algorithms, because even if there is a break, it might not actually mean that there's a land cover change. It might just mean that there's a particular disturbance or a dry year or something like that. And there are several options, for example, to look at the magnitude of the change. So if you find that it's not interesting to have low magnitude changes, you can just filter them out.
Agricultural land for the very different, right? Especially with agriculture.
Yeah.
And so where is it breaks here? Or?
Well, one question I'll ask you is what your objective will be of your analysis using the stack of Landsat images, because if you do it for disturbance detection, it's more simple. But if you will use it for land cover change mapping and classification, it's a different objective. So, for example, in the savanna areas, shrubby landscapes, there you have a high seasonality, while in forest, the seasonality is a lot less. So depends a little bit what you want to do. So it's good to reflect about that. It might differ from vegetation type to vegetation type. Yeah. Yeah. Yeah, indeed. Indeed.
Yeah, the betterment of the soil. But he thinks kind of like GP actually, not the production. Want to see whether there's degradation. Degradation can be production over long term.
But what I then can recommend is to look first at individual pixels and time series and understand what you are looking at first and what you want to do with it. And then you can optimize the model fitting and optimize also the break detection. And then just understand a little bit first what type of data you got and what you want to detect.
Yeah. And to add, it's also nice that BFAST is really a method that is based on data, which means that it doesn't matter what data you actually input. So it could be NDVI, but it could also be GPP. It could be land cover fractions. We just need numbers that change over time, and it can handle it, and it can detect breaks and give you all the interesting statistics out of it. But indeed, So yes,
All
so
sorts. Yeah.
yeah, so
can
sinusoidal is the default, yes, but we also have the seasonal dummies, so you can say how many intercepts per year you want to model. So it's really then data-based. And yeah, as you said, in agricultural areas, for example, you actually expect more dynamics. So that's why at the moment, you still need to have some expert knowledge of the area to say that, okay, we actually should have more dynamics or less dynamics to properly model the area. But if our experiments with automatically determining like this order and the fits from the data is successful, then it will make it also a bit easier to run it really on a global scale without needing to kind of tune the parameters.
Yeah. That's the basic test that I did at the whole start in 2010. Yeah, it's very robust to noise. Yeah. And even then, no, that's what it's designed for, to deal with outliers, etc. And you could also use it for outlier detection, etc. But yeah, there's another question.
Yeah.
Yeah,
exactly. So I would just, because we are already 15 minutes
running
over
time, so good.
Yeah, I also had a question. So the system takes care of the queue. So so I was also waiting for my question, but actually, in the meanwhile, I think Dainius answered it. I wanted to ask, for example, for forest, what would be the best index and maybe area and the sensor to detect it, but you more or less already covered it. So yeah, I will just use the time to say, yeah, thanks a lot for a great talk. It's amazing actually to see how this work you done, Jan, actually made amazing impact later, and it's great that we have Dainius now to take over with BFAST Lite and developing further the algorithm. So well done, and that's just comment from my side. And for other people, you should queue now again, guys.
There was one question, feel free.
Yeah, very short question. First of all, really interesting work. I was just curious about the dependence that you guys have right now in selecting what's the wave function, right? So like could be sinusoid. You said that you had many other options of wave functions, right? I was wondering if you guys, and perhaps that's what you mean by like the application of machine learning to automate that step, right? To use, for example, LSTMs, recurrent neuronal networks, or even transformers, right? Which like are showing really great performance on that. If you guys are currently, or like if you consider perhaps using that.
I can answer that. So again, these are like two separate steps. One is the change detection, and the other one is the land cover classification. And in our group at Wageningen University, we are actually very actively trying out the deep learning techniques to see also, do we even need, in that case, to run the change detection using BFAST, or whether deep learning methods can by themselves detect these kind of anomalies. And so far, it seems that still BFAST is useful, and the output from BFAST can also be used further in machine learning to actually even better detect what kind of, for example, land cover we have and how it changes. So it's actually a synergy.
Right, Dainius, Jan, I had a quick question more of a technical nature. So you showed some integrations with public clouds. What about actually making the software deployable on HPC, so traditional HPC, and how would you maintain that? That's the first question. Second question is, do you anything about continuous integration and say benchmark tests to be included with the software when you do deploy?
Well, so we have different versions of BFAST. So just going back to the list. So we have the GPU versions running on Python. We have the reference implementation in R. And there's also the ones that are running on the clouds. So the packaging would be a bit different for the different versions because they have different dependencies. So we are mostly working with the R version. So we know exactly how to deploy that. And it has relatively minimal requirements, actually. So running that on an HPC would not be difficult. But of course, you would probably want to run the Python GPU versions to actually make it fast. And then there might be more dependencies. Indeed, you need to run Futhark and PyOpenCL. So we would need to ask the people who are implementing it in Copenhagen University.
Yeah, Copenhagen, and now yeah, he moved to Copenhagen.
Yeah.
I think what I think the real problem is that most, let's say, non-experts, say in this domain, say technical administrators on big systems, they would have to deploy this, right? They're not going to deploy directly from GitHub. They're not going to find that any secure. And also having different versions of R on different systems may lead to all kinds of issues. So packaging your software according to international accepted standards, including continuous integration tests and benchmarking tests, we think would be very important to get this wider deployed.
Yeah, so here also you can see actually that on Sapal they have a user interface that shows how to use the BFAST GPU version. So they're just deployed quite well, but yeah, I don't know the details. But yeah, I agree that it's very useful to also see how it performs and also compared to the other ones. We have some research done into that. So there have been some benchmarks, but of course, different clouds also have different performance. So.
Yeah, just last comment on it, and then I'll let Giuseppe talk. Is that sure?
Just very brief question. Yeah. Maybe we can follow up on some questions during lunch.
Yeah.
But thanks for your comment and suggestion. We follow up on that.